So welcome, Moulay Barkatou from the morning. So we will see how we compute the simple forms of first-order systems.
Thank you, and thanks, I say, for the invitation and the opportunity to give this talk in this conference. So it's about simple forms of first-order linear differential system, and it's a joint work with my former PhD student, Karol Basha, who's now working at the Lebanese University. So then, when studying differential systems, the Moser and superreduction forms play a basic and important role, and they in particular give useful information on local invariant of a system at a given singularity. For example, the nature of the singularity is given by Moser form or Moser algorithm. And if you are interested in other information like integer slopes of the Newton polygon, and then the super-reduced form enter into play. These Moser and super-reduced forms play also a role in the computation of formal solution of the system around singularity. They are also used in the computation of global solutions such as rational solutions over C of x or even over hyper-exponential extension of C of x, and solving or finding exponential solutions of a given system. And they, in fact, the super-reduced form are too strong for what we in general want to get. So this I introduced so-called key-simple forms. They are weaker forms, and the talk today is about how to compute them directly without passing by reduced form. By the way, the reduced form, super-reduced form, gives these two key-simple forms. So in this talk, I will present this method, give an estimate of the complexity and compare it to this super-reduced algorithm, and I will show how this can be used to find the formal invariant for system at its singularity. So the main results are published in a joint work with Karol Basha in GSC, Journal of Simple Computation, last year, and extension to differential system of a hyper-exponential extension of C of x and application to computing integrals on this kind of extension has been done in a joint work with Clemens Rapp, published in ISAC 2012. So, I don't know if you can see the light is okay for me. Okay, so I'm considering, let me first explain what case-simple forms are, and how to compute them. So I'm considering systems, I will put it here, of this form. So theta is the derivation here, and the system is in, maybe I didn't use notation in a, K is, so I suppose that I have a system with the singularity at x equal to 0, a differential system. So I will consider the system written in this form, A, Y, and the matrix A has coefficients, so it's a matrix of size n and has coefficients in. Okay, here even in the ring of formal or series, and okay, this C could be a constant field Okay, this is the notation, and here the Q is called the rank of the singularity of Poincare rank of the system. So given such a system, it's known that it has a basis of formal solutions that can be written in this form. So this has been mentioned yesterday in a talk by Suzy in the adieu session for those who were there. Anyway, any element of this basis can be written in this form. They are exponential term, exponential to the q sub I of t. T is a root of x, so we need ramification in order to solve completely the system. Q is a polynomial in 1 over t with algebraic number coefficients. Lambda sub I is a algebraic number, and z sub I is a vector with entries that are polynomial in log of t with coefficients that are power series into. Given us such a solution, if it is okay. By the way, they refer to this part as the exponential part of the solution. And if this q sub I is non-zero, then the degree with respect to x, which is a rational number, so it's the degree with respect to t divided by the ramification here, is the slope of the so-called Newton polygon of the system. And when q sub I is equal to 0, then this is called a formal regular solution. And then it means that the Newton polygon of the system has a horizontal side, have a slope 0. The Newton polygon of the system is defined as the Newton polygon of any scalar differential equations that is equivalent to the system obtained by the method of cyclic vector. So, so this Newton polygon cannot be obtained immediately from the system. This is the one of the problems with systems. Yeah. So for the definition, it's a Newton polygon of any scalar differential equation associated to the system. And so this is why it is important to have tools that enable us to find information. For example, what is the Newton polygon, or what is at least its shape, whether it is when it is so the Newton polygon. Suppose that people are familiar with this. When you have a differential scalar differential operator, so of degree n, then you have just to, so the I sub I, A sub I are, we can assume that they are in they are power series. Then for each I, you just mark the point valuation of I. I'm working here with the theta derivation, and then you get quadrant like this, and you form say a Newton polygon. It looks like. So V is the x-adic valuation on this ring, and the slopes of the Newton polygon are the degrees of these Q polynomials. Okay, and we are interested in particular in the non-ramified exponential parts. This means when you do not need roots of x in order to solve, and these non-ramified exponential parts are important when you are, for example, looking, if you start with a system in C of x, looking for exponential, hyper-exponential solutions, then if you look for solutions in this form, and you want to determine the U, when you look at the expansion of U as long as there is at each singularity, then the singular part is exponential part, a formal exponential part at this singular point. So question is, okay, given a k between 0 and q is the concurrent of the system, to determine whether this k is a slope of the Newton polygon and get the associated Newton polynomials. Okay? So this information are obtained directly from a scalar equation, but for a system they are hidden and we want to work in order to get them. So the approach here is that the idea is very pragmatic. We want to start it from the system, get this kind of information directly from the system, from the few first coefficients in the expansions of the matrix A. Okay? As for the scalar case. For the scalar case, you need only to draw this Newton polygon, you need only to know the leading term of each A sub I. Okay? Okay, this is, you need only to know the valuation. And but for a system, all this is hidden and you want to find it. So the trick is, okay, you start from such a system and you multiply on the left the system by a convenient matrix, D here, diagonal matrix, with powers of x, only power of x that can, you fix k, okay, excuse me, and I denote by theta sub k. So theta sub k is the derivation x to the k plus 1 d over dx. Then you can, in a trivial way, rewrite this system in this form. So now we work with this new derivation, and d and n are matrices with power series coefficients, okay? Taylor series. Okay? There is no meromorphic term now here. Okay? Then it is easy to see that if you have a solution of this form, formal local solution, exponential integral of w z of x, w in this form, okay, polynomial in 1 over x of degree at most k plus 1. Then when you plug this in the system, in this system now, you get this necessary condition that d of 0, alpha is this term here, plus n of 0 z0 must be equal to 0. As z of 0 is non-zero, then the determinant of this matrix pencil must be equal to 0 at alpha. Okay? So you get the following proposition. If the determinant of this matrix pencil is does not vanish identically in lambda, and if it has at least one non-zero root, then k is the slope of the Newton polygon of the system, and the non-zero roots of this determinant are exactly the roots of the Newton polynomial associated to the slope of the system. Now remember that this Newton polynomial is not given from the outside on the system. Okay? And you can get, so there is a very simple situation. If you do this rewriting, so this is immediate, there is no computation here. Okay? And if you are lucky, I mean if the determinant is non-zero, then you have this information, k is a slope of the Newton polygon, and you get the what's called characteristic equation associated with the Newton polygon or the Newton polynomial. So this leads to the definition. So what is a case-simple system? A case-simple system is a system for which the correspondent determinant is not identically zero. Okay? So that is a case-simple system. Okay, so this notion has been introduced by myself and years ago, and is useful to compute rational solutions, as I said before, exponential solutions and other kind of closed form solution. So the question is, the problem is that if you do this rewriting, you are not guaranteed to get a determinant that is non-zero. Okay. This here is an example. If you take this example here, So here Q is equal to 3, and so K may have the value 0, 1, 2, and 3. If you take, for example, K equal to 1, and you do what, okay, so you multiply by this, each row here by a convenient power of x in order to get rid of the denominators, in fact, of the singularity on this side. Then you get this system with this matrix. And now if you compute the corresponding pencil matrix, you get this. In this case, this is a constant matrix. There is no lambda, but in general, there is lambda is involved. But you can see here that these two columns are collinear. So this is a singular pencil. So the system is not one simple. So we can, for this system, rewriting this system in this way doesn't give the information whether one is a slope or not. Okay. Now, if a system, I come back to my original system here. If it is super reduced, I didn't say what is super reduced for those who don't know, but I will tell a little about this in a few seconds. So if a system is super reduced, then it can be written as K simple form for each K from 0 to Q minus 1. So this, in that sense, super reduced is stronger than simple system. Okay. So if given a fixed K, integer K, how to detect whether K is a slope of the Newton polygon or not without applying this super deduction algorithm? I don't want to apply it because it's it costs more. Okay. Anyway, want to do this directly. So for those who are not familiar with this, just very quickly, what are super reduced form? So again, the same system. Q is the Poincare rank, and A0 is the residue matrix of A. It's supposed to be non-zero. So you take any I between 0 and Q minus 1, and then let n sub I be the number of the rows of the matrix A of x here, which have valuation x and valuation equal to I. Okay, so you just count the rows with valuation I for I from ranging from 0 to Q minus 1. Then you associate to this system the quantity n sub Q of A, which is given by Q and the n sub 0, n sub 1, n sub Q minus 1. Okay, this generalizes this number of Moser that some of you saw yesterday in the talk by Suzy. This is not a formal invariant of the system, but if you look at the minimal quantity m sub Q among all the element of the orbit of the system under the action of Genet here, then this mu is invariant. And when the m is equal to mu, this means when this quantity that you obtain directly from the system is minimal, the system is said to be super reduced. Okay? And what is very nice is that you have an algebraic criteria which enables you to know whether the system is super reduced or not. So n sub 0, n sub 1, n sub k minus 1 are, as I mentioned before. You form this R sub k, okay, for each k given between 1 and q. Then you introduce these polynomials. By the way, this depends only on the few first coefficients in the x-adic expansion of A. Okay, so this is a derivative that you can compute directly from the system. Then you have the following. First, these are polynomials in lambda with coefficients that are power series. Okay, this is why you choose RK in this form. And you have the following. The differential system is super reduced if and only if these two polynomials, all these polynomials from 1 to q, theta sub, okay, there is a problem with the notation. Oh, it's not the same theta. Okay, theta sub q is this, does not vanish identical. So you have an algebraic test. This is super reduced. So
I
So can you go back to the slide?
Yeah.
It looks like it's essentially saying the determinant is not 0 for k equals 1.
Yeah.
That's the same thing. Only the
Yeah, this
you don't
is
need to
the
worry about that.
determinant.
You don't really need to worry about the x to the rk in that definition. It's strictly the determinant that's non-zero.
No, because this is, no, we take x equal to 0 here. This is not, this is singular and x. Okay. Any super, as I said, any super reduced system can be written as a simple system. Here is an example, but I have to hurry. Okay, this is an example. You know, here if you compute theta 1, take k equal to 1, and you compute theta 1, it turns out that it's equal to the constant 10 here. So this is a super reduced system. And if you rewrite the system as I explained at the beginning, in the form d plus n, d theta plus n, you get a pencil that in this case is non-singular, and the determinant is the same. Okay, but if a system may be simple without being super reduced. This is the important thing. So here is another example now. If you compute for the pencil, you get a non-zero determinant, so this system is simple. However, the correspondence system written in this form, if you compute the theta 1, it's 0. So this is why I said the notion of simplicity is weaker than the notion of super reducibility. Okay. So how now to compute this simple form? So we act by equivalence transform on the system. So now I consider system of this form, d of x, theta sub k plus n of x, and two such matrix differential operators are said to be equivalent if there is s of x and t of x, two invertible matrices monomorphic power series entries, such that d tilde and d are related by this relation. Okay, so this means you have to can multiply on the left by any matrix invertible, and you are allowed to do change of basis. You know, you have an unknown function y. So the multiplication by t on the right amounts to a change of basis, change of unknown function y equal t times. Okay. So this I can skip. This is too technical. So now consider a system which is written this form. Okay. And I suppose that it's not simple, and I want to transform it into a simple system. Without any loss of generality, I can suppose that d of x, this is just for convenience for the presentation, that d is in Smith normal form. In the algorithm, we do not need to compute a Smith normal form for d. But you can always, you know, up to unimodular transformation, we can suppose that d is a diagonal matrix of this form. So here, x to the 0, r times, and then alpha, the alphas here are integers satisfying these inequalities. Okay. So anyway, when you start with a system like this, you immediately get a diagonal matrix on the left. Okay. But in what I'm doing, I'm considering here a general system. You know, D is not necessary. So we associate with this system what I call is K multi-rank, which is a collection, the untuple here, okay, of the variation by rows, okay, the alphas. This alpha of D is the multi, right, and its length will play a role in the what follows. So the main theorem is the following: given a system of the form I mentioned before, it is possible, there exists, and they can construct two invertible matrices U and V that are in fact, okay, they are supposed to be formal power series, but in fact they are polynomials. the first one, u is a polynomial in 1 over x, and its inverse is a polynomial in x, which means that it's a polynomial in x with determinant which is again a polynomial in x. Okay? V satisfies the same condition in the other side, okay, such that the obtained equivalent system, so delta u dv, is simple, so we can reduce any system to a simple system by polynomial transformations. This is very important for the algorithmic problem. And this new system has a rank, a multi-rank with length less than the original system. Okay? And let me just show you quickly how to do this for in a simple case. So in fact, the idea is to work on the pencil L of lambda, which is, we start with a pencil like this, which is singular, and do linear algebra on this pencil. So we can always arrange that the pencil is written in this form, and then we look at the so-called lambda-free columns and rows, some rows and some columns that don't depend on lambda. If, for example, the columns that don't depend, that are free of lambda, have rank, are not of full rank, then we can decrease the quantity length of modulo of alpha. Otherwise, we have to do some transformation to go back to this case. So the idea is like this. And in the case when the lambda-free columns or rows are linearly dependent, so this situation I mentioned before, the transformation is very simple, and is given here. We apply a transformation T of this form, so gamma can be computed explicitly, etc. And we can decrease, so we see this is a constant matrix, and the diagonal matrix with power here of x, and the gamma is a positive integer, and the alpha of d is decreased by gamma in this case. So it's really simple. Then by repeating at most alpha of d, this procedure, we either obtain a system with a multi-rank with length 0. In that case, we have a case-simple system, or we get a system with alpha, the length different from 0, but the lambda-free columns or rows are linearly independent. Okay? And the system is case-simple and we are done, or they are linearly independent, but the system is not simple. Okay? So here is a, how much time, right?
Not very much.
The usual answer. Okay, this is an example. When you see, if you form the pencil here, so you have so this is the constant columns. By the way, all of them don't depend on lambda. They are collinear, these two, for example, and the system is singular. And if you apply this constant transformation, then this diagonal transformation, then you get a new system here. And it turns out that it still be singular. And you repeat this kind of transformation again. At the end, we get a system with a determinant which is equal to 1. So this means that the system is 0 simple. Okay? But as the determinant is constant, we can say that 0 is not a stop-of-linear polygon. Okay? So this is the general case. It can be reduced to the case before. So as I have time, I skip this. Okay. So we can always, by this kind of transformation, just elementary transformation, compute a k-simple system. The complexity estimate of this algorithm is given here in terms of the size of the system, the multi-rank, the ranks of the multi-rank of the system. So as we work with systems that are power series, we need to truncate these power series up to some other new. This is new here. And in order to be sure that we compute what we want, this new must be big enough. So it is enough to take new. This is not a trigger. It's not bigger than the ranks of the original system. Then the complexity is here. So omega is the exponent of linear algebra. So omega is between 2 and 3. So you see this. And if you compare this to the complexity of computing, super reduced form, this is the complexity for super reduced form. The notation is, so Q is Poincare rank. Okay. Nu is more or less the same. This is the same. Okay. And n is the size. And you see, okay, this alpha can be bounded by n times Q. Because the worst case, all the rows have the valuation Q. So the length of alpha is exactly n times Q. So you have, say, n to the 4, n to here, n to the cube. So the difference is that this is it depends. When Q is bigger than n, and if you are interested for n fixed, this is quadratic in Q, okay? While this is linear in Q. And if you are interested in n, this is n to the power 5, okay? That's new. And this is it, n to the power 4. Okay? So I think it's something. Thank you.
Just a quick question from anyone. We'll do an open discussion in half an hour, so we can ask more detailed questions then. Alright, so we'll continue with the next talk, and there will be time for questions afterwards.